Hi Math 23, my name is Raviv Murciano-Goroff, and I'm going to be doing proof 9.1 for you today. First I'm going to read the question to you. So, to start, let W be an open subset of Rn+m, and let f be a function that goes from W to Rn. Let f of c be constrained to be equal to 0. And furthermore, we're going to assume that the derivative of f of c is onto. And with all that in mind, then the question asks us to prove that the n+m variables can be ordered so that the first n columns of df of c are linearly independent, and that df of c is equal to a composite matrix of A and B, where A is an invertible n by n matrix. So basically, df of c is equal to this composite matrix of A and B, and what it wants us to show is that A is invertible and that it's n rows and n columns. And we'll do that first. Second, it says let a point C be equal to the point AB, where A are the n passive variables and B are m active variables. We'll draw a diagram to make that a little bit clearer. And let G be an implicit function from a neighborhood of B to a neighborhood of A, such that G of B is equal to A. So in other words, G is a function where if you feed it active variables, then it's going to give you passive variables. And with all that in mind, then it wants us to prove that, that dg of B is equal to minus A inverse composed with B. So dg of B is equal to the negative inverse of A composed with B. And first I'm going to draw you a diagram just so that you have a sense of what's going on. So here's a point C. This is in Rn+m, but we're putting it onto the plane. C is really A passive variables, and B are going to be our active variables. And we also know from the question that this point is within a neighborhood called W. And finally, we know that this is all taking place within a function that is equal to 0, that's constrained to 0. So here's our point, here's the neighborhood, here's the function that constrains it. Okay, with that in mind, we're going to start the proof of trying to figure out how to show this by examining df of c. Well, what do we know about df of c? We know that the function f goes from W to Rn. So we know that we can write it out as having n rows. And we know that it's onto, so we know that there's going to be n linearly independent columns. So we know that there's n rows, n linearly independent columns. We also know that we start out in Rn+m. So that means we're going to have n dependent columns. And just for shorthand, then we're calling this matrix, this part of the matrix A, this part B. But what we notice here is that with A, well, if that's n linearly independent columns, then this forms the basis for the image of this derivative. And we also notice that, well, so A is n by n, and we notice that it's onto, right, because because these are n linearly independent ones and they're forming this basis, so we know that they're onto, and we know that they're n by n. So if it's square and it's onto, this is all what A is. A is square, A is onto, and that implies that it's bijective. And what do we know about bijective functions? Well, we know that if it's bijective, then it's going to be invertible. So we just showed that A is n by n and that it's invertible, and that's the first part of the 9.1 proof. Now to the second part. Okay, first we're going to talk about the function g. So, as I said before, just to remind you, g of b, g of the active variables, gives you back the passive variables. In addition, we know that when y is very near b, then we can do the same thing. We can put in the active variables and we get out the passive variables. So, so this is what we know about this function g. And we also know that we have m active variables, and again we have n passive variables. Okay. Next, we're going to talk about the function g tilde. So g tilde, or I should really say, the function g tilde of c is going to be equal to g no tilde of y and y. So this is just a function that just splits things into the active components and the passive components. That's all that this function does. But we can take the derivative really easily, and when we do that, then, well, we're going to end up with two components. On the top, well, what's the derivative of this? It's just the derivative of that, so it's dg of y. And what do we have on the bottom? Well, this is going to be the identity matrix. And we know that this is the active component. We know that there's m active components, so we know that this is Im, and that there's m rows. And on top, we know that this is the passive components. This is the n rows up there. So this is pretty good, but with this setup, knowing what this derivative is, let's erase this and start at the top. Start at the top so that we have some space, because we're going to try to get at that derivative so that we get at the proof. So let's start with the composed function f of g tilde of y. Now, what is f of g tilde? Well, g tilde is going to give us back a point c that's on that constraint line. And we know that f of c is always going to be equal to 0 because that's the constraint. So if we know that this is all equal to 0, that's a good start, but now we want to take the derivative of this. So if we take the derivative, then we end up with, using our chain rule skills, and actually I'm going to switch over to using b in here because I'm taking the derivative at a specific point. We know that this is going to be equal to 0. Okay, so both of these things look kind of familiar. So this kind of looks like what we did in the first stage. That's n by n, and this is m. And this looks like we did in the second stage. And this is n rows, and this is m rows. And we know that this is composed together. So what happens when we multiply these? Or when we compose these two matrices? Well, the A is going to be composed with the dg, so we know A dg of y. We know the B is going to go with the identity matrix, M, and that's just going to give us B. We know this is all equal to 0. So this is starting to look very easy to deal with. We move the B over to the right side, and we apply the inverse of A on both sides. And what do we get? Well, we get dg of... Why do I keep putting the y back in? Sorry, guys. dg of b is equal to negative A inverse composed with b. And this is what we were trying to prove. Is that we move that over, we apply the A inverse on both sides, and we've shown that the derivative of g at b is equal to minus A inverse composed with b. And that's proof 9.1.